In this video, we're going to take a look at the motion of planets and satellites in the context of circular motion and applying what we know to be the universal law of gravitation. Gravitation is sort of like centripetal acceleration, and in fact, Einstein's general theory of relativity says you can't really tell the difference. If we consider this classic movie 2001: A Space Odyssey, we were presented with an image of a rotating space station, like a giant hamster wheel. And if you can imagine people as the hamsters, because of the rotation, they could actually stand, theoretically, could stand on the rim and then get up, because the centripetal force would be pushing them inward. It'd be very similar to the normal force that we experience. And if you can get this radius and the speed just right, then you would experience an acceleration of 9.8, which we could call artificial gravity. It's not really done in practice. The International Space Station doesn't look like this because of cost and also because of the speeds and physiology required. It's really not just, it's just not a good fit for humans. Right, so what about this? We're on this spinning planet. How come we don't fly off? Well, Isaac Newton, again, building on the third law that forces have to come in pairs because they're interactions between two masses, and that, well, if you've got gravity, you also have to have two masses. Whether it's an apple falling in an orchard and the two masses are the Earth and the apple, or it's the moon in its orbit around Earth, which again, two masses are the Earth and the moon, that they're both going to feel the same force, but in opposite directions. And the magnitude of that force is represented by the universal law of gravitation, which again, proposed by Isaac Newton, since he understood that the third law says you have to have two masses. That's why two masses show up in this formula for force. And the distance between their centers squared, which has this unique property that, and you take the limit as r goes to infinity, that's equal to 0. And then finally, g, which is a very small number, telling us that gravity is a very weak force. It helps get the units to match out. So Isaac Newton couldn't determine g. He really didn't have the experimental setup to do it, but Cavendish in the 19th century could figure out how to do this, and simply said, if you take two large masses on the end of a long rod and let them stabilize for a long time, and then bring an apple A into close proximity to the other mass, that we can see it move. So if, oops, sorry, went ahead. So if this universal law of gravitation is telling us what our weight is, but we would use our own mass in calculating what this weight is, then if we set these two equations equal, we can actually solve for what 9.8 really means. And 9.8 meters per second squared is really based on the mass of the Earth and its size. You can see there's a slight variation between different locations on the Earth. It's actually greatest at the North Pole, because the Earth is an oblate spheroid, and the distance from the center of the Earth out to the North Pole is smaller than the distance out to the equator. So gravity is actually a little more intense at the North Pole, being closer, so the gravitational force is stronger. And so now we really come to a better sense about what weight is and what weightlessness is, because of the normal force. So if we put something in a stable circular orbit, what that means is that you just have to get going. You got to get going real fast. And as we imagine an altitude, how high up an orbit is, then the actual radius of that orbit is going to be the sum of the altitude plus the Earth's radius. So we just have to remember that from a problem solving point of view. Now, if we have gravity causing something to be in a circular orbit around the Earth, but the centripetal acceleration is v squared over r, then we can set these two equal. And we can come up with a couple of conclusions from this formula where v equals the square root of g mass of the Earth divided by the radius. So conclusion number one, it doesn't depend on the mass of the satellite. So we can continue to grow the International Space Station bigger and not have to worry about adjusting its gravity. The ISS is in a low Earth orbit, which means that it does encounter a little bit of air resistance. And so periodically, it's going to need a little boost in order to get back up there. Its altitude ranges between about 180 miles above the surface of the Earth and about 240. So at the time, because it's so close, it's actually going really, really fast. But anything at that same orbit is going to have exactly the same speed. All right. Well, what else can we draw from this? That's definitely one thing, but as the distance gets further away, the speed required for a stable orbit becomes less. So the moon is going much slower because it's pretty far away. It's about 245,000 miles. And it takes 27.3 days to go all the way around the Earth. Whereas the International Space Station goes all the way around the Earth about every 90 minutes. And so the ISS people feel weightless because there's no normal force. Gravity would normally be pulling, would be pulling down on you, and the force of the floor would be pushing up, supporting you. So that's what gravity feels like. But gravity is busy just keeping the International Space Station moving in a circle. So it doesn't have anything extra left over to pull you down onto the ground. And that's how come a spinning space station would feel like artificial gravity, because then you have an extra acceleration associated with it, the spinning part. Yeah, so weightlessness is just lack of a normal force, and that's actually pretty common. So now, a quick recognition of Kepler's laws. Johannes Kepler was an astronomer, actually an astronomer and astrologer who lived about 200 years before Isaac Newton, and came up with some observational laws. So these laws don't really explain anything, they're just observations. And one of his key observations is that the motion of the planets are elliptical. So that means the definition of an ellipse is that the distance between any 2 points is always staying the same. And if you imagine if you had a loop of string and 2 tacks and a piece of cardboard and you went around that loop, you get an ellipse every time. Each one of those 2 points is called a foci, and then the gravitational center would occupy one of those foci. So the motion of all the planets and all things in stable orbits are ellipses. Now the law of equal area says, kind of gave Isaac Newton some hints, is that if we take a radius vector from the sun out to the position at day 1 and out to day 2, it's going to sweep out an area that's consistent with whatever that time period is. In my case, 1 week. Then at positions 3 and 4, because it's a lot further away, then that would take more time to get there. So we expect the speed of the satellites to be minimal when it's further away. And then it's time for Kepler's rules of ratios, but we'll come back to that. So there you go. Those are the 4 big forces in the universe. So there are only 4. These are the only 4 forces that act at a distance. Other forces like pushes, pulls, tension, that kind of thing, they act by touching. Right. So it's really, from our daily, it's just electricity and gravity. All right, so soon to come, we're going to be some videos around problem solving. So best wishes. Keep up the hard work.